All right, for Unit 5 review, numbers 6 through, I actually think it's 21. Let us look at the relationship between the wrist circumference of a woman, that's the explanatory variable, and her body mass index, BMI, in kilograms per meter squared. We use the health data and the printout here, which was created in Staccato, to create the following graphs and statistics. The explanatory variable x is the wrist circumference, and the response variable is BMI. Okay, so here's our graph and our data with the sample size, the variables defined, correlation coefficient, the regression equation, R squared, and the standard error. So this is SE. All right, so now let's see what our questions are. Number 6, use the scatter plot of the correlation coefficient R to describe the strength and direction of the linear relationship. To answer that question, we go back to the number line we saw in section 5B. That tells us moderate, strong, weak, and negative, positive correlation. R is 0.5870, and on that number line, that corresponds with a moderate strength, whoops, sorry, wrong page. In a positive correlation. So it's a moderate positive correlation. It's positive because it's going up from left to right. It's a positive number. And it's moderate because that's where it lands on the number line of between 0 and 1. So for number 6, our answer is use a scatter plot and the correlation coefficient to determine the strength and direction. So there is a positive, I'm going to say actually moderate, positive relationship, correlation. Okay? Linear correlation. So okay, now number 7. So we're going to look at that scatter plot again, estimate the scope of the x values, and put those answers below. So the scope means I look at the minimum x and the maximum x. So if I kind of look at the lowest x value, go down to the x I see that's about 4.2. And the maximum x is right on this line of 5.8. So my scope of x goes from 4.2 to 5.8. Okay, that's the scope of x. Number 8, what is the slope of the regression line? Remember, that is not R. R tells us the strength and the direction of the slope, but it doesn't tell us the slope. Slope we get from the regression line. That's going to be the number that's attached to the x. So the variable that Staccato uses, that uses to show slope is B1. So this is the slope right here. So 10.9407. What was it? Sorry. 9407. And slope, the meaning of slope in context is always going to be the increase or decrease in y for 1 unit increase in x. So in this case, we're looking at BMI and woman's wrist. So for every inch increase in a woman's wrist, the BMI goes up by 10.94 kilograms per meter squared. For every additional 1 centimeter in the woman's wrist circumference. No, that's not right. I'm not sure how to spell that. Let me just go back. Circumference. Okay. We see a 10.9407 kilograms per, what is it called? Meter squared. Increase in BMI. Okay, that's my slope sentence. Now going on to number 9. What was R squared? Convert that into a percentage. And then for number 10, we're going to write a sentence about it in context. Whoops, darn it. What did I do? So our R squared is right here. Whoops, wrong color. Sorry. R squared is right there, and R squared converted to a percentage. That gives us 34.46%. And R squared explains the amount of variability in the x-axis that is explained by, in the y variable that is explained by that x. So in this case, we have 34.46% of the variability in BMI, or woman's BMI, is explained by the woman's wrist circumference. Forgot already, is that right? Yeah. Okay, number 11. List 3 confounding variables that might influence the BMI of a woman other than size of her wrist. These answers can certainly vary. Some that I can think of off the top of my head might be muscle mass, weight, height. Okay. Does this study prove that the size of these women's wrist causes them to have certain body mass index? Hopefully, as soon as you saw that word, causes, we're not proving anything about cause here. So, no, just because we can prove that it's correlated does not mean we can prove causation. Explain why. Correlation does not prove causation. Number 13, what was the standard deviation of the residual errors? What unit does the standard deviation of residual errors have in this problem? So our standard deviation of residual errors is down there in green. Oh, sorry. In green. So that's 5.058. Sorry, 5.0568. And the units are the same as the y, units in y, because it's a measure of the residuals, and the residuals are a distance in y. So 5.058 kilograms per meter squared. 5.0568. And explain two meanings. So the first meaning is the average prediction error is 5.0568. And that's one. And the second one is the average distance, vertical distance, the points are from the regression line is 5.0568 kilograms per meter squared. So those two meanings of standard deviation are in unit 5E, page 251. So read this section about those two meanings right here. Okay, going on to number 15. Does the residual plot above on the left show a V shape, or is it evenly spread out? And it's pretty evenly spread out. But if you notice, the right side goes all the way up here to all the way down here, where on the left side there's one point here, so you can see kind of a fan shape here where the dots kind of fill in. So even though it is relatively spread out, there is a bit of a V shape, not too much of a pattern, but a little bit of a V shape here. So this one will say there is a V shape. 16, does the residual plot above on the left show a curved pattern? No, no curve, just that V shape. So that's in our favor, so no curve. What we want for the most accurate prediction equation, we want no V shape. We want just a complete random scatter. So having the V shape indicates that our equation may not be the best predictor. Is the histogram of the residuals bell-shaped? Again, we want our histogram of residuals to be bell-shaped and completely scattered. But when I look at this, it's not really bell. And here's our zero line right here, and it's not really centered there. It's not that's not really the center of the graph. It's not the highest bar. There's not really a bell shape here. So I'm gonna say no. It's not bell shaped, and it's not centered at zero. So it's not a great predicting regression line. With the V shape residuals and the non-normally distributed residual plot, residual data, not a great predictor. So let's see. So, but we are going to use that regression. So even though it's not a great predictor, it's still what we have. So for 19, we're going to use a calculator and the regression equation to predict the body mass for a woman and her wrist circumference of 4.5. So to do that, we plug in for this x value. Instead of x, we're going to rewrite 4.5, which gives me, so 4.5 here, and everything else is just rewritten the way it is. So that's that times the 4.5 taken away from. Now remember your order of operations. So we need that multiplication first. So 4.5 times 8.367 gives me 37.6515. And I want to subtract that from, if I hit enter, I see that's in my history up here on my calculator. So I'll have that in my history. So I can clear this now, and I can subtract that number from the 48.802. 48.802 minus 37.6515. And that gives me 11.1505. It doesn't say where to round it, so I'll just leave it like that. My units are Y, so I'm protecting BMI. So that is kilograms per meter squared. Okay, number 20 in the previous problem, how far off is our BMI prediction on average? Our average is the average prediction error, or the standard error, which was 5.0568. So that's actually on number 13, but it's also on our printout right here. 5.0568. So that is 5.0568 kilograms per meter squared. So on average, I'm off by about that much when I make that prediction. Will this formula give an accurate prediction for the body mass index for a female child with a wrist circumference of 3.1 inches? And I'm going to say no for a couple reasons. First of all, we saw that the histogram is not bell-shaped. A histogram of the residuals was not bell-shaped. It was not centered at 0. We saw the scatter of the residuals was fan-shaped. So those are indicators that our equation is not very accurate. But even more importantly, is the fact that we're looking at a circumference of 3.1 inches, and our scope is, let's see, in scope, where did we answer about scope? It was between 4.2 and 5.8. So if our scope is from 4.2 and 5.8, then we're looking at an extrapolation here. So, no. 3.1 inches is outside the scope of X. This equation is not meant to predict the BMI for such a small x value. Anything that's not within that scope of x. So while we could still use that equation and make that extrapolation, it would have a larger prediction error. So the further and further we get from the scope, the larger our prediction error would be. So this prediction error is really only for within that scope of x. And that wraps it up for the Unit 5 review.